You still need to get it done?
It's done except for those two parts. It doesn't take a long time. I just don't know how it's going to be.
Yeah, it's kind of,
If you don't have you have to grab like the eigenvector or whatever.
Okay, let's begin, everyone. This is the summary of the topics that we went through in week 5. So we have done all of these. Okay, let's begin. Please quiet down so your neighbors can listen. Right, the part that I color in magenta here is what we did, and we'll continue with the excitement. Okay, so last time I have applied what you have learned for the standard eigenvalue problem to solve for the eigenvectors of the generalized eigenvalue problem. And the method is the same, right? The method is to set the first coefficient to 1 and then find the second coefficient, right? So we do the same for the generalized eigenvalue problem. So here is my lecture summary. Let me zoom in to fit. Okay. And let's focus on this part here. And I have my handwritten notes with annotation after class that I mentioned to you that it's a treasure for you to learn because it's hard to rival my own annotation because I'm the one who do the speaking, right? So when I annotate, it's very difficult for any student's class notes to really rival the detail of what I wrote in. So please make use of this resource, as I mentioned before. And let me use a different PDF viewer so that I can zoom in and zoom out much easier. And what I just showed you
And the same with these.
I wrote it down right here. Okay, what I just showed to you in the daily lecture summary.
Right, well the speaker's already there.
I wrote down right here.
And I will put that there, that's fine, but, you know, on my...
Oh, sorry, not there, just below.
Wall,
And this is related to a question that Kyle asked. Okay, whether the eigenvalues could be complex numbers, right? And I explained by using second order differential equation, where you have 3 cases of the sign of the discriminant. But in terms of the eigenvalues of the matrix of the stiffness matrix that we are looking for, this is a very important property that for real symmetric matrices, meaning symmetric matrices with real coefficients, real meaning not complex numbers, then you would always get the eigenvalues to be real numbers. Okay? So here I pose down a challenge to students in class for a lot of active learning credits, and I wrote down that challenge down here. And I will put on Piazza. So please go on Piazza and contribute. And if you get it, let me put on the mask. Maybe, yeah, I cannot go down further. So let me do like this. Okay, this part here. So there are really 2 questions. The first question is, can you explain why a symmetric matrix with real coefficients always have real eigenvalues? Okay, this is the first challenge. Think about it. I hope that there's some excellent student in class who could explain and give an example. Type up on Piazza. I will put the question on Piazza. That's question number one. Question number two, which is related to the first challenging question or critical thinking question, is that can you concoct a 2x2 matrix? Let's keep everything 2x2. Okay, keep it simple. Keep it simple. Can you concoct or fabricate a 2x2 matrix with real coefficients, but with complex conjugate eigenvalues? So that would be an example that would really explain Kyle's question. You know, display a matrix with real coefficients, but with complex eigenvalues. Can you explain and give an example on Piazza? And right now I'm thinking about 5 active learning credits, but I'm flexible. If the answer is excellent, I could even increase the active learning credits. Okay, so this is a challenge to the class, and I do really hope to have excellent contribution. And with that, I would like to move on. And let's continue with, right now, I'd like to go back to section 53D. Okay, and complete the search for the eigenvectors. Right? You have seen the method. The method is set one coefficient to 1 and find the other coefficient. Right? So let me bring up section 53D. So we did this. We did this page as well. Okay, this is basically just replace in the general expression for the generalized eigenvalue problem. You know, this the numbers in the stiffness matrix in numerical values and the numerical values of the coefficients in the mass matrix. How many unknowns? The same question over and over again, right? At this stage here, you have only 2 unknowns because we already found the eigenvalues. Okay, the eigenvalues we have found before, and I have recall here. So now the next step is to solve for the first eigenpair, right? The first eigenvalue was already solved for, that's 4. You remember that there are 2 eigenvalues, right? 4 and 9. So beta 1 is equal to 4. And so at this stage, you really have 2 unknowns, okay? So let's move down further. All right, so now you move the right-hand side to the left. And so here is the matrix K minus beta 1 m times phi 1. Beta 1 is null, that's equal to 4. So here you have 2 unknowns, 2 equations. Can someone remind the class what was the important property of this matrix here? Stiffness matrix minus beta 1 times mass matrix. What was the important property for that matrix? The
Determinant was 0.
Determinant equal to 0. That means that it's singular, right? Can you invert this matrix? Can you find its inverse? You know, raise your hand so you get active learning credit. I don't care about whether the answer was right or wrong. Right? So someone new. It looks like you're new, the one with the hand. What is your team number and name?
All right, it's team 3.
Team 3? Yes, and let's see, what's your name? Sorry, what's your name, team? Like, oh, okay. So this is second time for Blake. I'll not get you. Please raise your hand next time. Okay, Blake. So, can you invert that matrix? K minus beta 1 n. The determinant is equal to 0, right? Like the Van was saying. So can you invert this matrix? No, you cannot invert it, because if you can invert this matrix, then phi1 would be 0, because, you know, so let me write down here. And the Van is team 6, right? The Van. Okay. So what I was saying is the following. You know, if you have a matrix, let's say you are solving A times phi equal to 0, right? And I define A as K minus beta 1 m. Okay? So phi would be equal to A inverse times 0. And if A inverse exists, then phi is equal to 0. That's trivial. You don't want trivial eigenvectors, because that is not useful. Yes.
So I know how to do the math and stuff to find eigenvectors and eigenvalues, but what do the eigenvalues and eigenvectors tell us?
Right, okay. So the question is, you can do the math, you can plug in numbers, but why do you use eigenvalues and eigenvectors? And that I have already explained in a previous lecture. I'll come back to that question. What is your team number?
8.
Team 8 and name?
Team 7, sorry.
Team 7 name?
Nick.
Okay, Nicholas. Okay, very good. So this is a good question to review here, because I did mention that. Okay, so a short question, a short answer to Nicholas' question. Maybe I let the class contribute for active learning credit. Why do you need to do the eigenvalue problem? 1, 2, okay. You already contributed. Maybe somebody else? Matt?
Find the frequency of the system.
Find the frequency. Yeah, you can also say that you can find the frequency by solving the eigenvalue problems. Yeah, the vibrational frequency. Yes. What else? You know, what's the goal here? The goal is we have derived the equation of motion, right? Two coupled equation of motion. Direct.
Use them to help solve ordinary differential equations.
Use them to help solve the differential equation. Yes, but how? 1, 2, 3. The band.
To uncouple.
Uncouple, that's it. Uncouple the equation of motion, because you have two coupled second order differential equations that you don't know how to solve, even after taking differential equations, right? In the course differential equations, mainly scalar differential equations. Here you have matrix differential equations. So the key is to uncouple, and I use the static problem to explain how to uncouple. Okay, it's in previous lectures. I'll come back to that. But let me continue with this here, because the determinant of A, and I'll come back to the uncoupling. We have to pass through that step. So if determinant of A is equal to 0, this is a 0 scalar, then A inverse does not exist. Meaning you cannot invert. Okay, and that's how you can find non-trivial eigenvectors. And the way you find non-trivial eigenvectors was explained in previous lecture. is to set one coefficient equal to certain number. Okay, let's motivate further. Okay. So now we say that, well, the determinant of the matrix A, which is K minus beta 1 times the mass matrix, is 0. You cannot invert this matrix. So therefore, you hope to have non-zero eigenvector phi1. Now you have how many equations here? How many equations? How many equations in this? Yes.
Two different equations.
Two equations, right? Two unknowns. What is your team number?
Team three.
Team 3 and name?
William.
William, I remember contributed before. So, while I do this, please think about it. You have two equations, two unknowns. Can you solve for these two unknowns? Somebody said yes? Yes?
Yes.
Yes, okay, what's team number? Team 3, and okay, well, team 3 is very active. What's the name? Paul. Right, Paul, team 3. Anyone else? Any other contribution? Yes or no? Right?
Oh, I contributed before.
Sorry?
I contributed before, just so you know.
Yeah, so, but you answer.
Just wanted to, yeah. I just wanted to know.
Oh, you just want, yeah, you can remind me after class. You know, yes, don't worry about that. Direct one's the active learning credit. What's your team number? Team 8, right?
Yeah.
Yeah, so we can do that after class, okay? Yeah, if I forget, you have plenty of time. Okay, any other answer? The answer is no. Why? Because the determinant is 0. Okay, so even though you have two equations, but actually only one equation is useful. Okay, because if the two equations are linearly independent, okay, you can invoke the matrix, right, and solve for the unknown. But here, these two equations are not independent because the determinant is equal to 0. So actually, you only have one equation, but two unknowns. So the method, as in the case of the standard eigenvalue problem, is to set one of those two equations to some numbers, okay? Any arbitrary number. One is a simple number to choose, and then solve for the other equation. Now you can select the first equation. You can select to. Yeah, let me bring this up. So the next step here. Is to set the first equation to 1 and solve for the second coefficient, right? The first equation is phi11, then you can solve for phi12. But like I said, you can set any of those two, one of these two coefficients to any numbers, okay? To any numbers and solve for the other coefficients. Now this is a more challenging question here. Why? And this I also explained before. Remember, once you found an eigenvector, when you multiply that eigenvector by any scalar, what happened to that new vector?
It's linear?
It's linear.
So it's just multiplied by a constant, so the next one...
Well, they are collinear,
Yeah, they're
meaning they are
collinear.
parallel. But what can you say about that new vector? Is it still an eigenvector? Yes.
Yes.
Yes. It's still the same eigenvector. I mean, it's still an eigenvector with the same eigenvalue. Okay. So meaning that when you found an eigenvector and you multiply by any scalar, it's still an eigenvector with the same eigenvalue. And that's the reason why you can select arbitrarily any coefficient to set to a constant. And that constant need not be 1, but 1 is a simple constant. So therefore, you can select that constant to be 1, the first coefficient. Okay. And then, so you can solve for the second. Right? You can solve for the second coefficient, and that's the number. Well, you know, I said 1 is a simple constant, right? But how about 0? 0 is even simpler than 1. Agree? Can you choose 0? Can you set phi11 equal to 0? Yes. Seems very appealing, right? But if you carry out the calculation. If phi11 had been 0, what would happen to phi12? 0. No. Do not choose 0. 1 is better. Because if phi11 is 0 and phi12 is 0, that's a trivial vector that you didn't want. Okay? You cannot use a 0 vector to do anything. Alright? So please keep that in mind. So here is the result. This is the first eigenvector for the generalized eigenvalue problem, Matt.
If we chose a different number than 1, say let's say 2, would it
Okay.
still be the same eigenvector, or is it a different
Okay, so
eigenvector
Matt
now?
said if he had chosen 2 instead of 1, then what happened to the result? Meaning that if you had number 2 here, okay, and you solve for phi12, then what happened to the result? And this is what I just said. And so if someone, Brennan. Yes.
The other eigenvalue will be double.
The other eigenvalue will be double.
Yeah.
Okay, anyone else? Anyone else?
Behind you. Up front.
Someone? Yes?
It'll still be the same, because you said that.
Still the same?
Eigenvector times scalar, it's still the same eigenvector.
Multiply by,
The same eigenvector with the same eigenvalues.
okay. It's a very good question, so I need to give Matt here. Remember, if I forget, just remind me after class, okay? Matt and Brennan is team 3 too. Okay, team 3 is very active today. Very good. Okay, and somebody else. Okay, if I forget, please remind me. Okay, so let's follow what Matt was suggesting. If you have 2 here, right? Then you have 2 here. Okay, then would be 2 here, right? And then you have the factor 2. All right, so the result would be what? Would be, so let's use a different notation. Phi1 with a hat so that it looks different. Then that would be 2 and 2 square root of 6. You can pull 2 out, and that's 1 square root of 6. I think, what was your name?
Jason.
Jason, yeah, Jason is team 8, right? Okay, very good, Jason. So, yes, Jason got it right. So, this, even though you have a factor 2, it's still the same. I mean, it is still an eigenvector with the same eigenvalue up there equal to 4. Okay. Let me remind you over here once more. Okay, if you have k, right, phi1 equal to beta 1 and phi1. Okay. So if you multiply phi1 by 2, and let me use the red color. You see, so this is phi1 hat, phi1 hat. See, so this relation says that phi1 hat is still an eigenvector. It's not the same eigenvector, but these 2 eigenvectors are parallel, collinear. Phi1 hat is parallel to phi1. It's differ from phi1 by a scalar. But you know, both phi1 and phi1 hat has the same eigenvalue beta 1, which is equal to 4. Okay, so that's really what it means. And you can also practice by setting phi2 equal to a number, and I mean phi12. Let's go back here to my notes. right? If you, instead of setting phi11 equal to 1, you can also set phi12 equal to 1 and find phi11, right? So, and you can choose any numbers, need not be 1. 2 minus 1,000, 1 million. All right? So that's very important. And now, that's it. Once you get the concept, the second eigenpair is exactly, the method is exactly the same. Right? To find the second eigenvector, you already know the eigenvalue, right? The second eigenvalue, beta 2 was equal to 9. We already found beta 2. Now we just need to find the corresponding eigenvector phi 2, and the process is identical. So here, again, set the first coefficient, phi21 equal to 1, because phi 2 has two coefficients, right? Phi21 and phi22. So set phi21 equal to 1, find phi22. You know, you can also, like I said, set phi22 equal to 1 and find phi21. That's fine too. You know, you can choose the first coefficient systematically. Okay, and so if you carry out the calculation, right, you get one equation to solve for phi22, because phi21 equal to 1 is already replaced there. One equation, one unknown. This is the result, right? That's the second eigenvector corresponding to the second eigenvalue beta equal to 9. Alright, is it crystal clear to everyone? The process has to be crystal clear. Like your colleague asked, let's see, okay, eventually I will come back to that, my handwritten notes. Of some lectures ago, maybe meeting 14. Let me try. Yeah. You see, I could not repeat this more, but I have to repeat. Please use this resource. It's not possible to write all my own notes. Okay? You can compare with your own notes, and so I have spent a lot of time explaining, fill in the words for you. Please use this to learn. And here is the explanation. Going back again, let me zoom out so you can even have a bigger picture, or even better yet, let me do this. Let me bring up two windows so I can put side by side. Okay. Yeah, here. I'm sorry, I need to learn your name again. What was your name again?
Nick.
Sorry?
Nick?
Nick, yeah, Nicholas. Yeah, you asked why we solve the eigenvalue problem, right? So here I took a static problem. This is a standard eigenvalue problem. We can decompose the matrix K, and on this side, yes, so you see, so here you need to review, okay? I will not go through this because I already explained. Then you can uncouple that system. And so this is the uncoupled system here, because lambda is the matrix of the eigenvalues, and that's diagonal. Okay? And so once you have that new uncoupled equation, and this is how you solve. Okay? So that's the motivation for the why you use the eigenvalue problem, to uncouple the system. Now, like I said, for statics it's easy, but not so for dynamics. Okay. So now let's do the following. Okay. me see, I should have, oh, maybe I forgot. Oh,
Yeah,
yeah.
yes. But the white guy, right? And it also is done for
Let's-
very slow motion.
Let me coach you how to solve the exam
That's
problem.
him right there.
This is practice exam. So in this, this is exam 1.2. So this is part of my continuing to develop good communication of ideas and facilitation of learning. Okay, so this is the statement of the problem here. You are given the stiffness matrix and you are given the mass matrix. Okay? And the question is, solve the generalized eigenvalue problem. And by now, you should know the method, right? The method is, what was the method? Well, you know, you see my exam style is that I break the problem into small questions. So essentially that's the hint. Okay, so if you just answer the small questions, eventually you solve the problem. So the first question is find the characteristic equation of the generalized eigenvalue problem to solve for the eigenvalues. Contribution. What's the characteristic equation? Yes?
Isn't that when you take the determinant of k?
Determinant of k minus beta m equal to 0, right? Team 7 or team 6? Team 7, what's your name?
Frank.
Let's say team 7, Frank.
Yes.
Frank, yes. Okay. So what Frank said is, now I want to do quickly, okay? You know the method, so and there's no need for me to keep rewriting the same thing. So all you need is just to do determinant of k minus beta m and set that equal to 0. That's it. Expand out, you have a quadratic equation, and that's called the characteristic equation. All right, we have gone through that just today and even the day before. Second question. Solve for the eigenvalues. Well, this is just solving the quadratic equation. No big deal. Next question. Find the eigenvectors. By setting, I even give you a hint, you know. And this time, I ask you to set the second coefficient to -1. Okay? Same method, but I just want to really intentionally, this is not just an exam, but an opportunity to teach, to tell you that you can select any coefficient and set it to any number. So here I chose -1. Okay? No big deal. Once you set the second coefficient to -1, you just solve for the first coefficient.
Do you mean there how we set the phi11 equal to 1? Instead you're having us do -1, or am I not?
Yeah, so here, okay. What I meant, so
I mean, how we
Maria,
just did in that one.
yes, Maria, please remind me to give you equal credit. So here you see phi1.
Mhm.
Yeah, maybe maybe let me write over here. What I was saying is, okay, you have phi1. You have phi1, which has phi11
Mhm.
and phi12.
2.
All I was saying in the example is to set phi12 equal to -1.
Okay, all right. So we're solving for phi11.
Yeah.
Whereas
Then-
in the previous example that we did, you had phi11
Right.
as equal to 1, and then we solved for phi12.
Right,
And then
and
we
here-
did the -4 over.
Yeah, for the
squares. Right?
second eigenvector, you would have you would have 2, phi2, phi21, phi22, and just set phi22 equal to -1. That's
Okay.
it. That's all I would say.
Yeah.
The second coefficient.
I was just rehashing. Okay.
No, that's good. That's very good because you have the class. Anyone who asks question actually have the class. Because not many. So Maria is team 8. And you did contribute before, not just now. That's excellent. Okay, so let's keep pushing on. So you see, the exam is really the same thing as in the report and in my lecture. It's really, no more than that. Okay, so next question is to find the normalized eigenvectors with respect to the mass matrix and verify their mass orthogonality. Well, this is new concept, so at least we did A, B, C, and now let's jump to the second question. Okay, and then we come back to the D and E of part 1 later because this is new concept. But here you can already do this part 2, at least the first few questions. So I'd like to quickly show you that. Okay. So the first question is to convert the generalized eigenvalue problem to a standard eigenvalue problem. Okay. Now here are the matrices. I'm asking you, and I hope for good contribution. How can you convert this generalized eigenvalue problem, meaning k phi equal to beta m phi, into an equivalent standard eigenvalue problem? I hope some student will read it.
Make the mass matrix identity matrix.
Yes. Go ahead.
Make the mass matrix identity matrix.
Like the mass matrix identity matrix. Very good, Brendan. How? Very good. You are on the right track. Divide by 2. Okay. So Brendan said, so here the mass matrix is 2 times the identity matrix, right? So all you need is to divide by 2. So therefore you can have 1/2 here. So that means that you have a new stiffness matrix. Call it K bar. Okay. So here, if you write 1/2 K phi equal to beta identity times phi, and that's the same as beta phi. That's it. And this is a new stiffness matrix you can call K bar. And so this is the standard eigenvalue problem for K bar, the new stiffness matrix. So that is no big deal then. So essentially, Brandon remember the definition of the standard eigenvalue problem, and that is really what is expected. What is the standard eigenvalue problem? Okay. So, and then the next question is even easier, right? The next question in part 2. So the first question is to convert a generalized eigenvalue problem to a standard eigenvalue problem. And this is simple, right? So get someone point out quickly how do you solve for the eigenvalues. I call it gamma 1 and gamma 2.
Isn't that what you were doing in your handwritten notes last
I'm sorry?
on Monday? These, the gamma 1s and 2s. Right? In meeting 15.
Yeah, I did show that before. But here, let me.
Or was it in section 53? E.
No, the method is basically take the determinant. Okay,
Oh,
so
okay.
let me, yeah, let me do this. Maybe I should write over here. K. Yeah, K phi equal to beta m phi. There are two ways you can do. Okay, the first, and m, remember that m is equal to 2i. Okay, so method one is to divide both sides by 1/2. Then you have okay. And now this is we call K-bar. So the standard eigenvalue problem is K-bar phi times beta phi. Okay, and so the eigenvalues are the same. So eigenvalues are the same.
Yep.
That's one way. The second method, okay, the eigenvalues of the standard eigenvalue problem are the same as those of the original generalized eigenvalue problem. Now the second method that you can do is K phi equal to 2 beta identity matrix times phi. Okay? Because m is equal to 2i, right? So instead of dividing both sides by 2, you merge the factor 2 with the eigenvalue beta and call this the new eigenvalue. That's gamma. Okay? So the second method, this is gamma. So the standard eigenvalue problem now is written as follows. K phi. Now you use the same matrix but different eigenvalue. Okay, so equal to gamma phi. So now, and we call that
Wait, can you
gamma
repeat what you just said?
is equal to 2 beta. Sorry?
You said we're using similar.
Yeah, let me zoom out so you see both methods. Okay, so what I'm saying is the following. You define 2 beta as a new unknown called gamma.
Okay.
Okay? Now gamma, when you write like this, gamma are the eigenvalues of the standard eigenvalue problem, right? This is a standard eigenvalue problem, but for the same original matrix K. Whereas in method 1, you have a new matrix, which is 1/2 of the original matrix K. You see the
You kind of just choose.
similarity and the difference? Yes.
So, let's say we were doing the problem that we have in homework with mass is 1.3. If we were doing that, the standard gamma would be 1.3 beta. Or
Can you say that again?
if the mass wasn't 2, like you had earlier, like if it was 1.300, 1.3, gamma would now be
1.3.
beta.
Well, you know, you need to follow the problem statement, right? Because the problem statement tells you that the mass matrix is 2 times the identity matrix, okay? If the factor was different from 2, then whatever that factor
Okay.
should be here, right? 1.3 if you like. But the problem statement says it's 2.
Right.
Don't use 1.3.
Okay.
Okay. Does it make sense to everyone? So, first method, the eigenvalues are the same, the eigenvectors are the same, but the matrix is different, right? The matrix is 1/2. Okay. Second method, eigenvectors are the same, eigenvalues are not the same. The new eigenvalue is equal to 2 times the old eigenvalue. The matrix K is the same. Meaning that once you solve this standard eigenvalue problem, you get gamma, then you find beta by dividing gamma by 2. Right? Okay? So, we did a lot of work today, and Casey gave me the timeout sign now. So that's what it means here, okay? This actually, I give you really, in this question here, I give you the freedom to choose whether you use method 1 or method 2. If you use method 1, then your answer for gamma 1 and gamma 2 would be the same eigenvalues as the generalized eigenvalue, okay, if you use method 1. But if you use method 2, then gamma 1 and gamma 2 is equal to 2 times the whole beta, which is the eigenvalue of the generalized eigenvalue problem. All right, and here in question C, let me close by this. Okay, again, deduce the eigenvalues beta 1 and beta 2 of the above generalized eigenvalue problem. If you use method 1, then beta 1 is equal to gamma 1 and beta 2 is equal to gamma 2. If you use method 2, then beta 1 is equal to gamma 1 divided by 2, beta 2 equal to gamma 2 divided by 2. All right? All right, so please, still have 4 minutes. And I think that should be good enough for a lecture summary here for the team lecture summary. And while I do the summary up here.
So that first problem right there was basically my whole question.
Yeah.
And I was like, holy shit. Like, that's pretty point problem.
What's your name now?
I'm Will.
Yeah, I will. Like, maybe next time.
Yeah, I'll finish those last two. Down to the last minute. Alright, now I gotta finish up my. Yeah.